Right, hello everyone. So this is what we're doing today. We're going to take the stiffness matrices for that 3-node, 2-element problem. We've already produced those, and we ended up with those at the end of the lecture just before the last one. We're going to expand them using the theory from last lecture. We're going to add them up together, and that's going to give us the global stiffness matrices. And we're then going to use those with some applied forces, some boundary conditions. We're then going to solve for the displacements of all of those nodes. I need to make a minor correction though. I'm going to be working today from 2 notebooks. We're going to be working from, this is the right one I think, yeah, let me bring this one in. So this one here is where we ended up with 2 lectures ago, or the lecture just preceding the one where we expanded things. So we end up with, let's just enhance the font size on this a little bit because that's easier to read now. Okay, so this is where we ended up with the lecture just before the last one. So we were able to pull in this connectivity table. We were then able to use it to this was just a function to produce that cosine matrix. We then were able to go through, we had the length, Young's modulus, cross-sectional area, and then we went through each element and we produced a fancy matrix, a 4x4 matrix based upon the cosine squared, sine cosine, and so on. And then I put down here, expand the matrix. Okay, so what do we do now? Well, how do we actually complete the next step? So we need to actually apply that step, which we did in the following lecture. And this is where I'm going to issue a little correction. So this here is the completely annotated version that I provided after the lecture. So everything in here in terms of expanding these matrices is correct, except for one thing. And it's more of the basic theory. So if I have my global stiffness matrix and I've got my global displacement vector, for example, if I've got m nodes, I could have UA, UA, BA, UB and UC all the way down to UM and VM. Okay, so not necessarily going alphabetically up to M. I'm just saying I've got M number of nodes. And in fact, I shouldn't say M, should I? I should say N. That's maybe where some of the confusion came in before. And then this would be FXA, FYA, FXB, FYB, all the way down to FXN and FYN. So this N here is the number of nodes. Which means that these two vectors are going to be 2n by 1. Which means that this matrix here is 2n by 2n, where n is the number of nodes. In the expanding theory that we went through, I made my expanded matrix 2 times the number of elements, and that is not correct. So let's bring that up here. So going through this matrix here, all of this theory is fine. I went through here, went through here, went through here. Here, this would need to change. So here I've got the number of elements. This should actually be the number of nodes. So we're going to change this in the example that we do. We're not going to change this text, this text here, because all that we pull out of here are going to be, I think, this bit here. We're going to borrow this. We don't care about the number of elements, number of nodes. And we're going to borrow this syntax down here, just this line here. Okay, so we're going to use this today. But when we get to the correct point in the problem, I'll point out that we should be looking for the number of nodes, not the number of elements. So let's go back to, not that one, this one. So this is where we ended up within this problem, and we can see that when I wrote this, I didn't have the fancy printing methods. So what I'm going to do is I'm going to go back to the matrix expansion version. I'm going to go to the top and I'm going to borrow this print matrix line because I think it's nice. I'm going to put this in the top up here, and I'm just going to run that top cell again, and I'm going to go down here because we're going to be printing out a lot of different matrices today. I'm going to get rid of that line here. I'm going to say print matrix Ke comment that out. And if I run this now, here we go. We've now got some big matrices. They're 4x4s, so they're big and they go off the side of the screen and I have to scroll them. But I've now got two 4x4 matrices. Okay, so now what we need to do is we need to work out how we're going to take these and how we're going to expand them. So this is the same notebook we've worked from before. We need to look at the number of nodes in this problem. So let's go back up to the top, up at the very top, and I went through here and this is how I worked out the number of elements. I'm going to go through and I'm going to put a new line in. The number of elements was given by the number of columns minus 3, because the first 3 columns were node, x and y, and then anything else indicated an element. And I'm going to now say the number of nodes is just going to be equal to the length of contable, and I remember that if I remember here, my heading node is actually node with a space after it. So I just remember that from writing this before. I'm going to say however many items there are in here, I've got 1, 2, 3, that's going to be my number of nodes. I could have picked X and I could have picked any of the elements as well, but I just happen to have chosen that one. So I'm going to say, I'm going to write this in here. This system has that number of elements. Again, this is an F string, so we're formatting it as an integer by saying I want 1 before the decimal and 0 points after the decimal, and I want it to be at F, so that's fixed precision. So then I'm going to say NN let's just check this works. So this system has 2 elements and 3 nodes, and we know that's correct for this problem because it looks like I haven't got it here, unfortunately. I've got it in another window, but we know what this problem looks like. So now that we have this number here, NN, that tells us how big our global problem is going to be. So we know that we've got K Q is equal to P. So we know this matrix here is going to be 2n by 2n, where n is the number of nodes, and I've called this in Python n for number of nodes. So what we need to do is we need to take each of those 4x4s and expand them into a matrix like this using the same methods that we used in the last lecture, making sure that the right part of each matrix was taken in accordance with these entries in the correspondent or the connectivity table. And then we're going to make this matrix. So we did it in 2 steps. Let's go back over to this notebook. The way that I decided to do this was we had this connectivity row. That would have just been a column from my matrix. Okay, so I called it, let's go over here. So here I've got 0, 1, 2. For this particular problem, I just said imagine that this column was 1, 2, 0, 0, 0. Okay, I've called it a row there. That's me being a little bit loose with vernacular. That's bad. But where I've gone through here, so we were able to pull this out. I got the number of elements that was really here. This should have been the number of nodes. That's a mistake in this original notebook. Again, this would have then been 2 times the number of nodes, 2 times the number of nodes. But what we went through, let's look at what we actually did here. I then took this line out here and I said, okay, I want to go from that 1, 2, 0, 0, 0. I want to take it to be 1, 2, 3, 4, and then 6 zeros after it. So we had a little piece of line here that I called concol to nodal. So I'm going to take this out and I'm going to put it, let's work out where to do this. Okay, so we're going to be working in this cell in the notebook from 2 lectures ago. We're working through here and I want to be able to call that matrix down here, that function down here. So I need to define that function. Let's just define it up here. Concol to nodal. press Shift and Enter, and then I've got it. So let's go down here. So we've now got these 4x4s. I want to take that connectivity column, which for this problem, the first one's going to be 1, 0, 2, and then it's going to be 0, 1, 2, and then I want to then use this function I've just imported called concols and nodal and just change it from being 1, 0, 2 to 1, 2, 0, 0, 3, 4. So let's go down here. Just remembering that the significance of those two things are, if we have an element, say we'll call it element E, and we've got a 6-noded problem, element E might go from node 1 to node D. What that means is that when we transform the stiffness matrix into that 4x4, the 4x4 corresponding to element E would have this KE, and this would have UA, BA, UD, and VD. So there are twice as many displacements because we've got an X and Y than there are nodes. Okay, so I need to take this 1, replace it with a 1, 2, 0 to a 0, 0, 0, 0, the 2 becomes a 3, 4, 0, 0, 0, 0, and we have that function to do this. So we're going to use this. So let's call it, now I called it node, what did I call it before? I called it nodal row, I think, so let's just see down here, do I call it that down here? I called it nodal rows, yeah, let's call it nodal rows in here. Which means I now need to be able to extract that column, and it is actually, I think it's just this line here, it's the connectivity table, it's just going to be the column name which we've already pulled out, we've already got this here. So let's get rid of this print command, I've got an extra set of parentheses around here, and let's just check I get the right thing out. Let's do print nodal rows. There we go. 0, 1, 4, 5, 2, 3, 4. Yeah, that's right, that's correct. Okay, that's good. That's fine. So we've now got those out. Those are the, because it does this in, sorry, it did this in 2 steps. I sort of forgot how I got that to work. So this function up here is actually skipping a step. So this function here, nodal row would be the one where it turns it from 1, 2, 0 to 1, 2, 3, 4, 0, 0, and I then just pulled out the indices. I sort of forgot what I did last lecture. Okay, so let's go, we're in this same workbook I've just been working from. Let's go through this. So we're down here now. I've now got the nodal rows corresponding to this table. Now that tells me, if I get my 4x4, that tells me where that 4x4 goes into the expanded version of that, so, and everything else is going to be 0. So what I need to do is I need to make an empty 2n by 2n matrix. And we're going to call this K expand. So I've now got that 2 by nn matrix in there, and I'm now going to put those values into it. And the syntax we had to do to use this, I always forget this syntax, I think it's np.ix. Yeah, so we said, okay, well, once we have that nodal rows line, we can take that and we can use it to put it in here. Now, I've been a little bit naughty with my nomenclature here. I called this an uppercase KE for the matrix up here, which means I've either got to change this to an uppercase or change this to a lowercase. I will I will call this uppercase. I should really, which means I need to change it here as well. Okay, because this is 4x4, so it's in global notation, so it should be an uppercase K. So if I now try and print this, let's do print matrix. There we go. So we've now got some 6x6 matrices. We can see this first one corresponding to element 1. We've got UA and VA, nothing at UB and VB, and then something at UA and CA. And we remember element 1 was the one going from A up to C. And there's element 2, which it says goes from node B and ends at node C. It has a 4x4 transformed stiffness matrix. And then when we expand this, it's got things at B and C. And that makes sense because it went from B to C. So we've got those matrices now. Now all we need to do as we're going through this loop that's looping over those elements, we just need to add these matrices onto each other to produce the global stiffness matrix. So before this loop, I'm going to make an empty zeros matrix. Sorry, an empty stiffness matrix. Make empty. K is equal to np.zeros 2 times nn, 2 times nn. So it's the number of nodes, not the number of elements as I'd written previously. And then what we want to do down here, we're going to say add this to the global stiffness matrix. So I could write this, I could say K is equal to K plus K expand. But I can also use a good bit of Python syntax. This, I can just say, take the previous value and add it to it. So I do plus equals, or equals plus rather. I think that's right. Yes, that's right. So it's an equals plus sign here. It means we take the previous value and add on this new thing to it. So what this here is saying K is equal to K plus this bit on the end here, okay? So once we're out of here, I can now print out that global stiffness matrix. So let's have a look at it. Nope, it's not that, so I've got the syntax wrong then. So it is plus equals. And let's try this again. Of course it's plus equals, that's me being silly. If plus equals means K, take the previous value and add it onto it. I previously had equals plus. All that would have meant was K is equal to the positive value of whatever we put into it. Okay, so plus equals, this is the same as writing okay, that's what that line means there. And I realized that I'd made that mistake because when I tried to print out the global stiffness matrix, it was just equal to the expanded version of the previous one. So we can now see when we get our global stiffness matrix out, we've got a 4x4. We've got elements at A corresponding to A. We've got elements at B corresponding to node B, and we've got elements at node C corresponding to node C. We've also got something connecting A and C and something connecting A and B. We haven't got anything in these ones here, so we haven't got anything in these items, and these are because we don't have an item, we don't have an element that's connecting node A and node B, so that's why we have zeros in there. So we've now got our global stiffness matrix for this problem. So we need to work out how we can solve this problem. So looking at the values in here, I know this is correct because I've solved this problem before, but let's think about now, how could I look for, say, the displacements at node C and the reaction forces? sorry, now that we have the global stiffness matrix, I'm trying to think about what I'm saying as I'm writing it. Now that we have the global stiffness matrix, we're going to see that it's a symmetric matrix again. So if I try and take the inverse of this matrix, I won't get a nice number. So let's have a look. mp.linalg.inv k doesn't like it, okay, because it is a singular matrix, so we still can't do that. We need to apply boundary conditions to this problem, and that's how we're going to solve it. So let's just remind ourselves what this problem is. I don't have an image of this to hand, so let's just redraw it. Okay, so let's say we've got 10 kilonewtons on the system here. Nodes B and node A, they can't move. That's our boundary condition. That is a homogeneous boundary condition. And we're going to set an input of Fcy is equal to minus 10 kilonewtons and Fcx is equal to 0. I've just chosen to set Fcy equal to 0 for ease of solving this problem. I could have set it to a value if I wanted, and we still could have solved this whole problem. So we apply these boundary conditions by recognition of the fact that, let's write these out here. This is my stiffness matrix in here. I'm not going to write the numbers in, but I am going to write UA, VA, UB, VB, UC, and VC. And that's then equal to FAX, FAY, FBX, FBY, FCX, and FCY. So these ones here are my constraints. These are constrained deflections. So we'll say this is QC, constrained. These ones here I'm going to make green, and we'll say these are active, these are able to move. This is no more complicated than how we've solved the simple problems by hand or how we solved it by hand before. I'm just formalizing some of this nomenclature. We've then got PA here, very similarly, and PC here. So these ones here are going to be our reactions, and these ones here are going to be the applied loading. And the way that we're going to solve this is exactly the way that you'll end up solving your homework. There are more complicated means that we can solve when we've got non-homogeneous boundary conditions, but this way will work for now. So we can appreciate this matrix here is a 6 by 6, and we're going to separate it down into some different areas. And let's say this is KCC, because it's the portion of the stiffness matrix that relates these constrained displacements to the constrained reactions, which are constrained forces, which are the reactions. We'll then say here this is K, and it's relating the active displacements to the constrained forces. So we'll say this is KAC, this is KCA, and this is KAA. This one here is the part of the stiffness matrix, which for this 6x6 would be a 2x2 that relates the active displacements, which is the bit that we want to know, and this applied loading here. And the reason why we like to set it up like this is because this bit here is known, and this bit here is unknown. So then we have a problem we can solve for these two bits that we actually know. Sorry, these two bits that we want to know based on the bits that we don't know. So we set this problem up as KAA, QA, equal to PA. Okay, so we then solve this problem here. And that's what we're going to do with this next bit up here. So I can't take the inverse of this matrix. I want to just extract the lower right-hand side of this problem. So again, for this simple problem, that's just going to be the 5th and 6th row and the 5th and 6th column. So let's get that stiffness matrix out of there. So that's, again, because Python starts at 0, let's bring the screen up so you guys can see what I'm typing. I've got rid of this cell was previously the one that gave me the error. I've now just got rid of it and said, let's extract the lower right-hand corner matrix. Okay, this is the one that we want to solve. Let's do print matrix KAA. Okay, so this is just the lower right-hand side of here. It's just taking these 4 terms and putting them out into their own matrix down here. We then need to make a vector of those forces. And so the forces that we said, we had Fcy was minus 10 kilonewtons, Fcx was 0. So that would be these two down here. So we're going to have 0 and minus 10 E3. Okay, so we've now got set up in this format, and I'm going to use NumPy's linear algebra .solve to solve this. There's lots of different ways we can solve this. I'll show you a few of the different ways. So that's going to be QA, the active displacements, is going to be equal to numpy.linearalgebra.solve Here we go. So we've now just got these two deflections out. Now this says that node C moves by just shy of 1 millimeter to the right, and it moves by about 1.5 millimeters down. And that makes sense for this problem. The problem, remember, we've got just 2 elements going up that way, and now we're pulling on them. It says that C moves to the right and it moves down, and that makes sense. And again, I know these numbers are correct. With these displacements now solved for, we then have our complete displacement vector, because we've just solved for UC and VC, and we know that all 4 of these, because these were the boundary conditions, we know those are going to be 0. So let's solve now for these unknown reaction forces. And the way we do that is by making the whole global displacement vector. This is going to be tricky actually. Let's do NP. Don't know if this is going to work. Let's try it. So what I've done is I've made my constrained ones, which is zeros, and I'm going to see if I can concatenate these two together. Is that going to work? Oh, it does. Okay, so this is now my Q matrix, or my Q vector rather. If I multiply this by my global stiffness matrix, it will give me my 6 forces out. So let's do that. Let me just show you the wrong way. If we do K times Q, then we get, we don't get anything if I print it that way. We get something weird here. We get like a matrix out, which is not what we expect, and that's because we don't know how to multiply these two things together like this. So I can either use NP dot, which should be like that. Or I could do P is equal to K, and then I use the @ symbol Q, and I get the same answer each way. So let's just do, here we go, and then I get my forces. So these forces here, I've got FCX 20 kilonewtons, FCY 20 kilonewtons. Sorry, that's not right. Why have I written C there? Those should have been A, sorry. I'm going top to bottom here. FAX is 20 kilonewtons, FAY is 20 kilonewtons, FBX is minus 20 kilonewtons, FBY is minus 10 kilonewtons, and then FCX, these were just the inputs, is equal to 0, and FCY is equal to minus 10 kilonewtons. So what we got out here is we got the inputs back out from this problem, which haven't come directly from us having put them in. They've come from us having solved the stiffness matrix and then multiplied the global displacement vector by them. Okay, so just getting these numbers back out shows that we haven't sort of made this vector here, our Q vector, incorrectly. And now what we can do is we can just check we've got equilibrium. So let's do the sum of forces in the x direction. Well, that's going to be equal to this one plus this one plus this one. So 20 minus 20 plus 0 gives me nothing. And let's do the sum of forces in the y direction. 20 minus 10 minus 10. I've got those forces correct. So the whole structure is in equilibrium. We've solved it now using completely finite element methods. Okay, so hopefully you guys have followed through as we've gone through this. I'm going to give you guys another notebook that explains this in slightly more detail. Let me just bring this over. This was one I actually wrote last year. So it's the same problem here. It uses some slightly different methods to the way that I've done it in class, because I always find different ways to do things. And this way actually solve the whole problem in symbolically and then add some bits onto the end of it and substitutes in those numbers. But we go through some of the LaTeX formatting has broken since I wrote this, but I'm not going to bother solving it. But here we go through, and I just included a little bit more detail in here. Okay, go through and I solve it slightly differently. So what I really want you guys to do is to go through with the lecture as I've gone through this and update your own notebooks to check that it works. And then if you want a little bit more supplementary detail, you can look at this applied one here. You can look at this. Okay, because this again solves it in a slightly different format. So what we've done now is we've taken the methodology that we've determined over the preceding lectures and we've used it to solve a truss structure. And what you'll note is actually this was a statically indeterminate truss structure. So we had 4 reactions and we were able to solve it without employing the force method or any of that stuff. So we've shown that actually using these methods can save a tremendous amount of time, as long as we're smart in the way that we apply them and we make sure we're doing them properly. We can't yet get the internal forces because all we've got at the moment is those nodal displacements. So what we need to look at next, and what we're going to do tomorrow, is how we determine the internal forces within every member. And then on Wednesday we're going to go through another complete example, and then you guys are going to be left to your own devices to complete your homework. So I hope you're all enjoying this finite element stuff. I think this module is really fun. I hope you guys are finding it at least 1/100th of as fun as I find it, which would still be pretty damn fun. Okay, have a wonderful week. 2 more lectures coming this week and a review at some point, probably on Friday when we find the time to do it. Okay, take care guys. Good night.